Hi there. Welcome back to our video series of Applied Machine Learning with KerasCV and KerasNLP. My name is Wei, and I'm a developer advocate from Google ML team. In our last video, we discussed how to use KerasCV to perform image data augmentation. In this video, we're going to go over another important computer vision task, object detection. Object detection is a process of identifying, classifying, and localizing objects within a given image. Typically, your inputs are images, and your labels are bounding boxes with optional class labels. Here's an example. In this image, the object detection model has not only classified the object as TV monitor, but also identified the 4 corner points of the bounding boxes around the TV object. On the right, you can see a sample model output, a class, and a bounding box. In reality, the input image may be more complicated and has more objects in it. In this case, object detection is done by generating many anchor boxes of varying shapes and sizes across the input image, and assigning them each a class label, as well as 4 data points to pinpoint the bounding boxes. So let's learn how to do this with KerasCV. We will start with basic object detection with a pre-trained classifier. Then we will train a custom object detection model. It's pretty straightforward to perform detections with a pre-trained model. Let's walk through it now. As an example, we're going to use the RetinaNet model pre-trained on the Pascal Walk dataset. Other than RetinaNet, KerasCV also offers YOLO V8 and YOLO X models for object detection. Note the XYWH bounding box format. XYWH stands for X, Y, width, and height, which basically gives you the top left corner plus the width and height of the bounding box. There's another format, XY, XY, which gives you the top left and bottom right corners to pinpoint the bounding box. To use the RetinaNet model with the ResNet 50 backbone, we need to make sure the input image size is divisible by 64. So we're going to resize the test image to 640 by 640 here. We map the class IDs to class names so that the KerasCV visualization tool can print out the class names for each object, along with the bounding boxes. Now we run inference and make predictions. As you can see, the model is able to detect 3 objects and predict their respective classes. But the object on the right is arguably a little bit hard to say for sure. If you're familiar with object detection algorithms, you probably remember something called NMS, non-max suppression. NMS is a traditional algorithm that solves the problem of a model detecting multiple boxes for the same object. It's quite easy to set up an NMS layer and pass it into the pre-trained RetinaNet model in KerasCV. Here as a demo, we are essentially turning off NMS layer by setting the IOU threshold to 1 and the confidence threshold to 0. And since NMS is turned off, you can see all these bounding boxes on the right. Now let's turn the NMS back on by changing the IOU threshold and the confidence threshold parameters. For context, raising the confidence threshold will cause the model to only output boxes that have a higher confidence score, while IOU threshold controls the threshold of IOU 2 boxes must have in order for one to be pruned out. This time, we get a much better and cleaner result. While running a pre-trained model may be sufficient for many occasions, there are cases where you probably want to train a custom object detection model. While it is generally challenging to set up an object detection pipeline, KerasCV is making it as easy as possible. So let's take a look. We first load the Pascal Walk dataset. We can visualize the dataset to make sure everything looks alright. It is super important to do this before proceeding because the bounding box format sometimes causes issues. Similar to image classification, we can also perform data augmentation for object detection. In this case, we're doing it in a bounding box friendly way inside of a tf.data pipeline. We can take a look at the results. For evaluation dataset, we're going to use vanilla resizing instead of jittered resize, which is random. And we visualize the results as well. Next, we unpack our inputs and prepare to feed them into the model. After that, we define the SGD optimizer. We use the COCO matrix for evaluation. Since computing this metric is quite expensive, we set the evaluation frequency to 20. Due to TPU compatibility issues, we're going to use a custom callback to work around them and perform evaluation. For example, focal loss places extra emphasis on difficult training examples. This is useful when training the classification loss, as the majority of the losses are assigned to the backend classes. Smooth L1 loss is used to prevent exploding gradients that often occur when attempting to perform the box regression task. Finally, we call the fit function, and that's it. It's quite some work here, but KerasCV is making it relatively easy for us. Before we wrap up, let's do one more thing as a bonus point. We're going to use Stable Diffusion to generate some images with KerasCV and then perform object detection on them. If you are not familiar with Stable Diffusion, don't worry about it. Think of it as a magic box that takes in a string and spits out amazing images. Our next episode will be dedicated to Stable Diffusion, so we'll have a chance of learning all about it. You can see how the detection results look on these stunning images. That's it for today. In conclusion, KerasCV allows you to perform object detection with a pre-trained model or assemble an object detection pipeline to train a custom model easily. Next time, we'll focus on image generation. Thank you.